Welcome back. Today, we're going to deep dive into something that sounds, I don't know, a little intimidating. At first, especially if you're trying to teach it to a seventh grader, matrices and 4D geometry.
Yeah,
Well, but we're here to break it down and make it fun and approachable for you and your homeschoolers.
that's right. We're going to explore these concepts with a focus on building a general understanding and showing how how do you use this math every day? So let's start with matrices.
Okay, so matrices. I remember them being these grids of numbers, but they always seem mysterious to me.
Yeah.
What exactly are they, and how can we explain them to a seventh grader without, like, their eyes glazing over?
Think of a matrix like a neatly organized container for information, a spreadsheet. Each number in the matrix has a specific place, like an address, defined by its row and column.
Hmm. Like a grid in a board game,
Yeah.
or the pixels on a computer screen.
And these grids of numbers, or matrices, they're used for way more than just solving equations. They're used in computer graphics to create those awesome 3D worlds in video games.
Oh, really? So when my kids are playing Minecraft or Fortnite, there's all these matrices working behind the scenes.
Absolutely. In fact, one of the coolest applications is in skeletal animation. Imagine a character's skeleton made up of bones connected at joints. Matrices help calculate the exact position and rotation of each bone, allowing animators to create incredibly lifelike movements.
Well,
It's pretty incredible. And matrices are also used in animation to morph shapes and create smooth transitions between poses.
So it's not just about creating 3D worlds,
Yeah.
but making those worlds come alive with movement and action.
But matrices aren't limited to the entertainment world. They're also powerful tools for analyzing data and finding patterns. Think about a social media company trying to understand how users interact with their platform. They can use matrices to organize and analyze massive amounts of data,
Yeah,
identifying trends and making predictions.
that makes sense. So it's like having a mathematical magnifying glass to help make sense of all that information.
And the applications, they go even further. Matrices are used in fields like cryptography, engineering, physics,
Wow.
and even music.
Okay, I'm starting to see how versatile these matrices are.
Yeah.
But before we move on, I want to make sure I understand the basics. You mentioned rows and columns. Can you
Yeah.
explain those a little more?
Of course. Think of it like finding your seat in a movie theater. You need the row number and the seat number to locate your spot, right? Similarly, a matrix has rows that go horizontally and columns that go vertically. The size of a matrix is defined by its number of rows and columns.
So a matrix with 3 rows and 4 columns would be a 3 by 4 matrix.
You got it. Now let's talk about some spiral types of matrices.
Mhm.
There's the identity matrix, which is like the number 1 in multiplication. When you multiply any matrix by the identity matrix, it doesn't change the original matrix.
Interesting. So it's like a neutral element in the world of matrices.
And then there's the zero matrix, which is filled with all zeros.
Okay.
It's like the starting point for calculations, like a blank canvas.
That makes sense. So we've got our basic matrix structure, and we've got some special types of matrices. But how do we actually do anything with them? I remember there being something about adding, subtracting, and even multiplying matrices. But it wasn't as straightforward as with regular numbers, right?
You're right, matrix operations have their own set of rules. Adding or subtracting matrices is pretty intuitive. You just combine the corresponding numbers in each matrix, as long as the matrices are the same size.
So it's like adding apples and apples, but you can't add apples and oranges.
Precisely. But matrix multiplication is where things get a bit trickier.
Is there a way to explain it simply without getting bogged down in the formulas?
Absolutely. Imagine you have a matrix representing the prices of different ingredients for a recipe,
Yeah.
and another matrix representing the quantities of each ingredient you need. By multiplying these matrices together, you get a new matrix that tells you the total cost of each ingredient.
Oh, that's a great example. So it's like combining 2 sets of information to get a new, more meaningful result.
Exactly. The way you multiply those matrices involves a process called the dot product,
Yeah, okay.
which combines rows and columns in a specific way. Don't worry too much about the details for now. The key is to understand that matrix multiplication is a powerful tool for combining and transforming information.
Okay, that helps. What about this whole 4D geometry thing? I can barely wrap my head around 3D.
I know it sounds pretty mind-bending, right? But remember how we talked about matrices having rows and columns? Imagine a matrix with 4 columns. Each row in that matrix could represent a point in 4D space.
Wait a minute. So are you saying that matrices are like a bridge between our 3D world and this mysterious fourth dimension?
Matrices give us a way to describe and manipulate objects in 4D space, even though we can't fully visualize it.
I'm starting to see how these concepts, as complex as they seem, can be broken down into manageable pieces.
And remember, the goal is to build a general understanding and spark curiosity, not to become experts overnight.
I love that approach. Now, I'm really curious to explore this 4D world a bit further. What exactly is the fourth dimension, and how can we even begin to wrap our minds around it? You mentioned that the fourth dimension is often represented as time. How does that fit in with the idea of a fourth spatial dimension?
That's a great question. It's important to distinguish between those two interpretations of fourth dimension. In physics, Einstein's theory of relativity treats time as a fourth dimension, interwoven with the three spatial dimensions to create a concept called space-time.
Okay, so space-time is like a four-dimensional fabric, where time and space are inseparable.
But in geometry, when we talk about 4D space, we're usually referring to a fourth spatial dimension, something that exists in addition to length, width, and height.
Okay, so it's like adding another direction to move in beyond the three we're familiar with.
Think of it this way. A 2D creature living on a flat surface can only move left, right, forward, and backward. It has no concept of up or down because those directions require a third dimension.
Like a character in a classic arcade game moving around on a flat screen.
Exactly.
Yeah.
We, as 3D beings, we have a similar limitation when it comes to 4D space. We can understand length, width, and height, but adding that fourth spatial dimension is where our brains start to struggle.
How do we even begin to wrap our minds around it?
One helpful approach is to think about shadows and projections. Imagine shining a light on a 3D object, like a cube. The shadow it casts on a flat surface is a 2D representation of that 3D object.
So the shadow contains some information about the cube, but not all of it.
Similarly, we can try to imagine the 3D shadow that a 4D object would cast in our space.
Okay, I'm trying to picture this. So a 4D object's shadow in our 3D world would be like a constantly shifting, morphing shape that we couldn't fully comprehend.
It would defy our usual understanding of geometry.
That's pretty mind-blowing.
It is. Now, one of the most famous 4D objects is the Tesseract, also known as a hypercube. It's often depicted as a cube within a cube, connected by lines that represent the fourth dimension.
I've seen those images before, but they always seem so abstract.
They are. But remember, that's just a 2D representation of a 4D object, trying to draw a sphere on a flat piece of paper. You can capture some aspects of it, but not its true essence.
So the Tesseract is like the 4D equivalent of a cube.
Yeah.
What kind of crazy properties does it have?
For starters, a Tesseract has 16 vertices, 32 edges, 24 faces, and 8 cells.
Wow.
Compare that to a cube, which has only 8 vertices, 12 edges, and 6 faces.
That's a huge upgrade. But beyond those numbers, what makes 4D geometry so different from what we're used to?
One mind-boggling concept is that in 4D space, two objects can intersect at a single point, even though they appear completely separate in our 3D perception.
Wait, what? So it's two ghosts passing through each other.
That's a great analogy. And get this, in 4D space, you could tie a knot in a closed loop of string without ever cutting the string.
Okay, now you're just messing with me. That's physically impossible in our world.
It is in 3D, but in 4D it becomes possible. These seemingly impossible feats, they highlight the limitations of our 3D perspective, and they make you wonder what other incredible things are possible in higher dimensions that we can't even begin to fathom.
I'm starting to feel like Alice falling down the rabbit hole. This whole 4D world is so strange and wonderful.
Yeah.
But can we bring it back to matrices for a moment? How do they actually help us work with these 4D objects?
That's where things get really interesting. Remember, matrices are all about organizing information and representing relationships between numbers.
Right.
Each row in a matrix can represent a coordinate in 4D space, just like a row in a 3x3 matrix can represent a point in 3D space.
So a matrix with 4 columns can be used to describe the position of a point in 4D space.
And we can use matrices to perform operations on those 4D coordinates, like translating, rotating, or scaling objects in 4D space.
So even though we can't visualize 4D space directly, matrices give us a way to manipulate objects within that space mathematically.
That's the power of matrices. They provide a framework for working with abstract concepts that are beyond our direct perception. And who knows, maybe someday our 7th graders will be the ones developing new ways to visualize and interact with higher dimensions.
That's an inspiring thought. But for now, I think my brain needs a break from all this dimension bending. Can we explore some more practical applications of matrices, something a bit more grounded in our 3D world?
Let's shift gears and delve into some real-world examples that highlight the versatility and power of matrices in fields like computer graphics, data analysis, and even music.
Can you give us some specific examples of how that works?
Absolutely. Let's start with computer graphics, since we've been talking a lot about 3D and 4D space. One of the most fundamental uses of matrices in graphics is for transformations.
Transformations. What does that mean in this context?
It refers to the way we manipulate objects in a digital space. For instance, when you rotate a 3D model in a design program or move a character in a video game, you're performing transformations. Matrices provide the mathematical framework for making those actions happen smoothly and accurately.
So when I'm designing a house in a 3D modeling program, and I want to rotate the view to see it from a different angle, there are matrices working behind the scenes to make that happen.
The program uses matrices to calculate the new coordinates of every point in the model after the rotation, and it does it so quickly and seamlessly that we don't even notice the complex math happening behind the scenes.
That's pretty incredible. It makes me appreciate the power of these tools even more. What about music? How are matrices used in that field?
Think about how digital audio is recorded and manipulated. Sound waves are essentially vibrations that can be represented mathematically. Matrices can be used to represent those sound waves and apply various effects to them.
So like adding reverb or echo to a recording.
Those effects are achieved by manipulating the sound wave data using matrices. They can also be used to adjust the volume of specific frequencies, creating equalization effects.
That's so cool. It's amazing to think that the same mathematical tools used to create stunning 3D graphics are also used to shape the sounds we hear.
It really speaks to the interconnectedness of different fields through the language of mathematics. And this is just the tip of the iceberg. Matrices are used in fields like cryptography to encode and decode messages in engineering, to analyze stress and strain in structures, and in physics, to model the behavior of particles and forces.
It's clear that matrices are much more than just grids of numbers. They're powerful tools that enable us to understand and interact with the world in ways we might not even realize.
And that's why it's so important to introduce these concepts to young minds, even if it's just at a basic level. Who knows, maybe one of your students will be inspired to explore these fields further and make groundbreaking discoveries.
I think the key is to present these concepts in a way that sparks curiosity and shows their real-world relevance. I have to say, this deep dive has been an incredible journey. We've explored the fascinating world of matrices, ventured into the mind-bending realm of 4D geometry, and discovered how these concepts are woven into the fabric of our technological world.
It's been a pleasure exploring these ideas with you. It's been a pleasure.
And to our listeners, thank you for joining us on this deep dive. We hope you've enjoyed the journey and feel inspired to continue exploring the amazing world of mathematics.
This is